Okay, we are studying line integrals. It's very exciting, right? Line integrals. Actually, today we will prove a theorem, a result about line integrals, which is the first of a series of results that I promised you last time, which relate integration in different dimensions. Okay, so let's talk a little more about line integrals. Last time we talked about line integrals of vector fields. Okay, so but actually this is not the only kind of a line integral that you can have, and so today we'll talk about other kinds as well. Let me remind you what we learned last time. Suppose that you have a vector field on the plane. As always, a vector field can be written in two different ways. You can write it like this, or you can write it like this. And you can choose whatever way you prefer, whichever way you like. So you're given this is a vector field. Okay? And in addition, you're given a curve on the plane. This is a curve with some, in this case, with two boundary points, but in general, you could actually also look at closed curves which don't have a boundary. So a line integral is a combination, is a pairing, if you will, is a marriage of a vector field and a curve. Okay, so it takes two objects to produce an integral. You need a vector field and you need a curve. Okay, and so that integral we write like this. We write it f dot dr over c, and we write it also we write it in the following way. Dr here also stands for a vector which has two components, dx and dy. Okay, and when you take the dot product of these two vectors, this one having these two components and that one having those two components, you produce p dx plus q dy. And then we can write it down more concretely in a way suitable for calculation by parameterizing the curve. So we write x is a function of some auxiliary variable t, and y is a function of some auxiliary variable t, where t is between some values a and b, where, say, this point will correspond to t equal a, and this point will correspond to t equal b. If you do that, you can actually write it as an ordinary integral, just an ordinary one-dimensional integral from a to b, with respect to dt now. But as always, there's sort of a price to pay, and the price to pay is that we have to replace dx by dt, but we can't just replace dx by dt. We write it as dx dt times dt. So this quantity is reminiscent of Jacobians, or even earlier in one-variable calculus, we always had this factor when we made a change of variables. And this kind of factors show up here as well, right? So the end result of this is that you get p dx dt plus q dy dt. And that's already an ordinary integral in t. So notice the difference between these two. Here I write this integral as an integral over curve, which is on the plane. But here I rewrite it as an integral over just the basic interval from a to b, just the basic line segment from a to b. Certainly this is much simpler than this, and we've been able to pass from this form to this form by using this parameterization. This parameterization, as I already explained many times, what it does, it really identifies this complicated curve with this simple line segment. Those are the formulas which describe how they are identified. So this is t equal a again. This is t equal b. And all the values in between correspond to some points on the curve. All right? Is that clear? Yes. Could I do one simple example? I did an example last time, right? But right. Okay. Let's do that. So last time I had an example which was actually slightly more complicated. In my example last time, I had vector fields defined in 3-space. But let me just simplify that example a little bit and get explain this in two-dimensional case. So example, let's say you have a curve in which x is equal to t squared and y is equal to t cubed. Okay, and so you have that's the curve, and t stays from 0 to 1, and then you have a vector field which is let's just say x times I plus xy squared times j. Doesn't matter. Just to illustrate this. Okay, so in this case, what is a line integral? You're going to have an integral from 0 to 1, which are these limits, and then you simply substitute all this stuff into this formula. So this is p, this is p, this is q, right? So you get this is p, and p written in terms of the t variable is t squared. Then you have to write dx dt. Dx dt is 2t dt plus. Well, if I want to write it exactly in that form, I'll just put the dt outside. Plus you put xy squared. Xy squared is what, t to the 8th, right? dy dt is 3t squared and then dt. And so then you get a very simple integral of a function in t dt from 0 to 1. Is that clear? Okay. So I will not do this calculation. It's easy. Right? So I'll just stop here. All right. So what do these integrals represent? So last time we discussed that this integral represents the work done by this vector field viewed as a force vector field, work done by a force field F in moving an object or particle along this curve C, right? So, and when we were deriving it, the way we derived it is as usual with integrals. We break the curve into small pieces, right? We break the curve into small pieces. We then approximate each piece by a line segment, right? So let's say this is I blow up one of those segments. So let's say that's this segment, right? Which I blow up on this board to make it easier to keep track of things. At a small scale, because the curve is smooth, we can approximate it well by a line segment, by a linear thing, okay? By a piece of straight line. And so let's say this is piece number I. This is a piece number I. There will be, let's say, in this case, maybe a dozen pieces, but eventually we'll make this partition finer and finer, so it'll be 1,000, a million, a billion, and so on. Right? So let's focus on one of those pieces. When we focus on one of those pieces, we have here we have, with respect to the x-axis, we have the distances delta x, delta xi, and here it will be delta yi. Okay? And then we will have our force vector field. And because we're on a very small scale, on a very small piece of the curve, it will be a good approximation to think that the vector field is just constant along this segment because it's very small. Right? So it's going to look like this, and so on. And so you will have some, let's call this vector fi. And so the work done, which as I explained last time, remember I was erasing things, the work done here is easy to find. It's just a dot product of fi and delta r. So the work, let's call it work number I, work done on the ith segment, is just a dot product of this vector, which is the red one, and this one, which is the yellow one. And this yellow vector is, we'll call it delta ri. It has two components. One is delta xi, and the other one is delta yi. So I want to dot these two things, fi dot delta ri. Both are vectors. Okay? And more concretely then, this is going to be the first component, which will be some pi times delta xi, plus the second component, qi times delta yi. So that's the work done, approximately. Approximate work. I should say, this is really approximate because we are making two kinds of approximation here. First of all, we're approximating the actual segment of this curve. It is curvy, even though it is very small, but it's curvy in principle. But we are approximating it by something linear. That's the first approximation we make. And the second approximation we make is that the vector field also varies in general a little bit along this segment, but we are assuming that actually it doesn't vary. So we pick a particular value somewhere in the middle, and we just assume that it stays the same along this segment. So this is the kind of approximation that we make at this point. But the idea is that as our partition becomes finer and finer, this approximation, the error of this approximation will go away. So we'll actually get the exact result. So the next step, in other words, is to take the sum. So take the total work, which is the sum of the work done on each of those segments. And that's approximately now equal to what? To f dot fi dot delta ri, which can also be written as the sum of pi delta xi plus qi delta yi, right? That's the formula we get. I'm essentially repeating what I said last time, but you'll see why. You'll see in a minute why I want to repeat this. So, as always with integrals, this sum, as the partition becomes finer, actually tends to the integral, what we call the integral. So that's how we end up with this integral. And what integral? Well, we'll have f dot what we call dr. So delta r under this limit becomes the differential dr. So we get f dr. That's this line integral which we are talking about now, precisely, as a total work done along the curve. And also you can also think in terms of this expression, which is a more detailed expression for this dot product. So that's how you get this second formula on the left board, which is p dx plus q dy. Right? It's the same thing. It's just writing the dot product in components. So that's what we've done so far, and that's called line integral of a vector field. And I think the terminology is a little bit misleading because it suggests as though line suggests that we're integrating over something linear, but we're not. I guess line here means to represent the fact that we're doing a one-dimensional integral. So something which is also, line is one-dimensional, so that's why we call it line integral. But in fact, I would rather call it a curve integral or a curve integral because we're really integrating over a curve. So what I would like to say now is that this is not the only type of line integral. Let's follow the standard terminology. This is the only type of line integral that we can have. As you see in this line integral, what we are doing is, at the end of the day, we are calculating an expression like this, where there are two types of terms. One has this form, some function times dx, and the second one is some function times dy. So this already makes you wonder, what are these dx and dy? What is it that allows us to insert them under the integral and make the integration? That's the first question. And the second natural question is whether there is something else like dx, dy that we could use potentially also to produce line integrals, or integrals over the curves. And the answer is that yes, that there are actually other ways to produce line integrals, which are also meaningful from the point of view of applications, which have a different interpretation though, not as work done by force. And in trying to generalize it, we simply have to go back and look at this picture one more time. So what is the structure of the integral that we obtain? Well, the structure of the integral is really dictated by what we've done at one of the segments, at the segment number I. What we've done is that we've taken the dot product between this vector fi and the displacement vector along this segment of the curve. But that expression came from physics. That was because we tried to find the work done by this force. But let's look at the result. The result is really the sum of these two expressions, pi delta xi and qi delta yi. These are really the basic expressions that we have written down for this I segment, which have eventually led us to consider those integrals. So if we want to generalize this integral, we should do it at this step. Once we write the i's term, essentially there's no choice. There will be a particular integral as the limit when we sum up over all I. Right? So we see, what are we doing? So we have this segment, and let's focus on this term, for example. So this term is a product of two factors. The first factor is a value of some function. So it's some number, essentially, but this number depends on the ith segment. So at the end of the day, when we take the limit, this will become a function. So it's some particular quantity which we attach to this segment. But the second factor actually has a geometric meaning. The second factor has something to do with the shape of this segment. It actually is the length of the projection of this line segment onto the x coordinate. Of course, somewhere in the background, I imagine the coordinate system, xy coordinate system. Okay, and so this is the projection of this vector onto the x-axis, whereas delta yi is the projection onto this vector. Right. So the way to produce this integral, in other words, is to combine two things. One is a function like p, and the other one is some length. And this length could be the length of the projection onto the x-axis, or it could be the projection onto the y-axis. And if somebody comes and chooses another coordinate system, for example, polar coordinate system, which would have instead of xy, would have r and theta, they could also take the displacement with respect to one of the coordinates of that system. For example, instead of delta x and delta y, you could have taken delta r or delta theta if you were working with polar coordinates. So in other words, there are many choices here. We choose delta x and delta y for two reasons. First of all, in this case, there is a very nice physical interpretation of the resulting integral. And second of all, our xy coordinate system is somehow the most basic coordinate system that we can have. There is, however, one geometric quantity, one length attached to this picture, which is somehow intrinsic. It doesn't depend on any coordinate, and that's just the length of this interval. So in retrospect, even though we've gotten now these very nice integrals, which have this very nice interpretations, the work done by force and so on, we can now go back and in retrospect see that actually perhaps the most natural thing to do, now that we're starting to analyze it in more detail, would be to take instead of delta x or delta y, just delta s, namely the length of the segment. Right? So this way we get a different type of line integral. Different type of line integral is obtained if we take instead of delta x or delta y, no, let's even say delta xi or delta yi, we take delta si, which is the length of the segment. The length of the segment. All right, so what do we get in this case? So in this case, let's call this delta si. And of course, delta si is nothing but the square root of delta xi squared plus delta yi squared, right? So how about taking instead of this expression, take the expression. In fact, maybe let me go on this board so that we can follow the analogy more closely. So take the expression instead of this one, take the expression put some fi, where f is some function, some number, well in this case some number because it's attached to the I segment, times delta si, which you can also write as fi square root of delta xi squared plus delta yi squared. Okay, so if we take the sum now of these expressions, this will tend to a different kind of integral, which will still be an integral over c, which will have f times dx squared plus dy squared. So then, of course, we ask, what does it mean to have such an integral? Well, to do justice to such an integral, we really should parameterize the curve the way we did here. So let's go back to this parameterization. When we parameterize it like this, we get this auxiliary variable t. So now our curve gets replaced for all intents and purposes by a simple line interval, which makes things much easier. Right? So we will end up with an integral, again, from a to b over this auxiliary variable. We'll have here f, where we substitute x as a function of t and y as a function of t. And then here I will make a trick. I will divide everything by dt and multiply by dt. Okay? But if I divide by dt, that means that under the square root I divide by dt squared. So I will end up with dx dt squared, dy dt squared times dt. You have a question? Why did I change it to delta s? Why are we doing all these integrals in the first place? Because we have to. No, because this is what we have to do in this class. But no, because this integral makes sense, and then you need it in applications. For example, if you want to calculate the work done by force. By the way, this is not the only application of line integrals. We'll talk more about them today, about the fundamental theorem. But for instance, if you look at the end of that section, 16.2, in the exercises, there's discussion of the Ampere's law. And Ampere's law is about line integrals of magnetic field caused by current. Say you have a current going through a wire, and this causes magnetic field. So you would like to know the force of that magnetic field, and you can find what the line integral of that magnetic field is by knowing the current along this wire. Okay, I'm getting to answer the question. Okay, this is the introduction to the answer. All right. So this was the reason. I'm explaining now a different type of integral, and I will explain now that this too has application to something meaningful. Okay. So, but you can think about it. You can think about these integrals from 2 points of view. One is a kind of utilitarian point of view, which means why do I need this? What is the situation where I actually need this integrals? And for this we have answers. For line integrals of vector fields, you have work done by force, for example. But more than that, for instance, Ampere's law can be understood in terms of line integrals. This type of integrals, as I will explain now, will allow you to calculate things like masses of wires. I'll get to this in a minute. Okay. So this is a utilitarian point of view. A second point of view is a more abstract point of view. We certainly know the utility of integrals in general. Okay. But so far, in one variable calculus, we would only calculate the integral of a function over dt. What I tried to explain in the last lecture is that you can only understand the most beautiful results in calculus by developing the most general possible integrals that you can take, the theory of most general integrals. So you can stand on the point of view of why are we doing. So I would turn your question around. Your question was, why don't we just stay with this? Why do we take delta si? Is it just to make our life more complicated? I would turn it around and I say, why only this? Now that we understand this, why not do something more general? You see, and then see if that has some interpretation. So the integrals I'm talking about are the most general integrals over a general curve on the plane. That's the answer. And this is one example, or perhaps, this example leads to this integral. This is one example. This is an example of an integral vector field, and this is another example. Okay, you had a question. That's right, you're right. So delta si is approximately equal to the length of the segment. When I wrote length of a segment, I was implicitly referring to this line segment, which was approximating my curve. But if you would like to think of delta si as the original one, then it would be approximate. ds, no, it's always ds is always the differential, right? So it is a linear increment. So the question is about approximation. Well, it's in some sense it's true. It depends on how exactly you introduce notation. But if you introduce in a certain way, you're right. That's what will happen. Okay, so I've given you this sort of a pep talk about the utility of integrals, but now I have to explain what is this useful for. And this is useful for calculating things like lengths, like the total length, for example. What is the total length of this curve? The total length of this curve is such an integral where the function f is 1. You see? So this is the point.